Sorry, I have a little nervous because today's title doesn't relate to climate. However, the global climate model of the CCliCS very similar to this weather model. So, my name is Chen. Those are my colleagues in the global team. So, first I would like to thank Professor Huang Xiongxu to give this opportunity to show the global forecast system of the CCliCS. So, this is the outline of today's presentation. First, I'm going to introduction of the global CCliCS GFS. Second, I will talk about the balanced bogus typhoon scheme and its performance. And third, I will talk about the developing work and the future plan. This table shows the model status of the operational center in the world. For example, ECMWF has upgraded to their model to TL1279L91 in 2010 January. The horizontal resolution is 60 kilometer, and vertically they have a 91 layer in sigma coordinate. The dynamic structure is semi-implicit and semi-Lagrangian plus spectrum. For CCliCS model, we have upgraded to 319L40 in 2011 in November. The horizontal resolution is 42 kilometers. This model is in sigma coordinate. This resolution compared is compatible to known gaps. However, they upgrade their model to Navy Chen last month. The resolution is about 37 kilometers. This model, I think, is a semi-implicit and semi-Lagrangian plus spectrum. Last year, we upgrade our model to T319L60. This model is in sigma p coordinate and vertically has 60 layers. This year we are testing this T511L60. The resolution is 25 kilometers. Okay. This simple flowchart shows the how the CCliCS GFS do operationally. We have three kinds of data used in this CCliCS GFS. First one is regular observation data. Second is when typhoon genesis, we do typhoon bogus. The third data we use is EC data, some of the layer we use. These three kind of data plus initial condition go into the GSI and then run forecast model. This is the status of the CCliCS GFS. For data simulation, we use 3D VAR GSI. For the model, I have shown previously slides. The forecast model now is 319L40. The other two is we are testing now. Hopefully we can run this 511L60 in the late of this year. For when typhoon genesis, we do typhoon bogus. I will talk about in later. For the physical parameterization, we have a soil model parameterization. The following are their reference. So we have soil flux parameterization, flux PBL, topography, gravity wave drift, cumulus parameterization, shallow convection, large-scale precipitation and radiation. Also, we do a real acceleration in stratosphere. In this table, the red color means these modules is come from NSAP. This table shows the observation data used in GSI. There are two kinds of data. First one is traditional. Traditional data, including surveys and sounding. For satellite data, all kinds of satellite data. The red color means they are used operational now. This table shows the amount of data used compared with the NSAP. For traditional data, we were 95% of the NSAP. For satellite data, we only use 60% of the NSAP. Totally, we were there 20%. The low panel is an example of the satellite data. Deep blue color is NSAP. Shallow blue color is CWB. You can see we use quite few of satellite data. This figure shows the score of operational model of the CWB GFS. This is 500 millibar high anomaly correlation in North Hemisphere from 1999 to 2012. The red line is the running mean of the monthly data, so you can see the tendency is going up. How about the L60 model and the operational model is L40? This left panel is the anomaly correlation of a vertical profile of anomaly correlation on day 5 forecast from June 1st to June 30 last year. You can see below 205 millibar the anomaly correlation L60 is better than the operational model L40, but above 250 millibar operation is better than the L60. However, in South Hemisphere, the L60 is better than the operation. If we do the temperature mean bias, you can see the L60 has a cold bias larger than L40. But for the Loomis square error, L60 is better than the L40. This is North Hemisphere. However, in South Hemisphere, L60 is better than L40 for the Loomis square error. And lower panel is U component. You can see L60 is better than L40 in both hemispheres. We are still working on finding out why this come out. Okay, next I will going to talk about how we do the balance, how we do the bogus typhoon. This scheme is so-called balanced bogus typhoon scheme. This is the ranking vortex formula we use. There are three parameters, which is maximum wind and the curvature of the outer wind, and third is the curvature of the maximum wind. Okay. In this typhoon report, we have only one information from this typhoon report. Is maximum wind. The other two we doesn't know, but we can use so-called 七级风暴风半径 to determine the B, and the central pressure to determine the maxima, the radius of the maxima. So this is the algorithm of the bogus. So first we find the typhoon from initial field, then remove typhoon, and then do bogus. How we do? Give an initial guess of the RM and B, so we can use ranking vortex to compute the phi, the wind profile. Then we solve the nonlinear balance equation to get phi, and then use a hydrostatic equation to estimate the pressure of the typhoon and compare to the central pressure of the typhoon of the observation. So if estimate typhoon pressure larger than the observation, then we go iteratively to, we modify RM and B and iterative to this. If the central pressure estimation is less than the central the observation pressure, then we stop and then use hydrostatic to compute the temperature field. So after we get the structure of the typhoon, we blend in with the environment. Then we do a nonlinear no-moment initialization to get a balanced field. So we chose the 6 ring around the typhoon center. So for each level, there are about 39 points for each level. And this is the analysis. You can see the warm core around strong wind around the eye wall, and the warm core is about 300 millibar. This is the Meihua typhoon using this scheme. You can see very similar to the analysis. We use 10 cases to test this scheme. This is the average typhoon track error. Use L40 operational model. You can see for 70 hours, the error is about below the 270 kilometers. Low number is the case number. Compare with the operational model at that time. The red color is the operational model at that time, and the green color is the testing model. So you can see this scheme is the result is quite good. So we operation this model and this scheme, and last year we upgrade our model to L60. So we compare this two model. You can see before day 3, L60 is better than L40 is better than L60. After day 5, after day 5 and day 4 is L60 is better than L40. So next I will going to talk about the developing work and the future plan. For data assimilation, we are going to use more satellite data. I will show you next. And second, we are developing the global hybrid data assimilation. Hopefully, we can operation in 2014 next year. For forecast model, we are going to upgrade our model to T511 L60 in the late of this year. Second, going to modify our physical parameterization. And then third, we are developing the semi-Lagrangian model. Hopefully can run this TL1151L80 in the maybe 2015. Also, we developing the typhoon ensemble track prediction system by using singular vector perturbation method. This figure shows the radiance data used in the CHI. Before 2012, we have only 6%. Now the red color bar, we have about 13%. In the near future, we will going to use the YACI and the airs. At that time, we will be about 70% of the NSAP. This is the result. If we use YACI data, we can get a better we can get a higher score of 500 millibar anomaly correlation. So for physical parameterization, we are going to replace the soil model to NOAA's service model, and we were going to replace cumulative parameterization by a new SAS. These two modules come from NSAP also. Also, we are going to add in a non-orographic gravity wave track parameterization. This module is written by ourselves. Okay. This is the track of operational model L40 and the L60 testing model, and the T511 L60. This is hopefully can operation the layout this year for this model. This is the resolution compared with the comparison between the T511 and the operational model. This is the case of the Sanfu typhoon. This is the initial time, tau equals 0, and 24 hours forecast. You can see this high resolution model can get a better result of the typhoon. After 48 hours and 72 hours, you can see this high resolution model can get a better result than the operational model. This is the this typhoon in May 23 is not get intensity, high intensity. So if we look the 2412Z, you can see the intensity of typhoon is increased. You can see the high resolution model can get a better result of the typhoon. After this is 48 hours, and this is 72 hours forecast. You can compare to the operational model, can get a better result. Next, I'm going to show the semi-Lagrangian and semi-implicity model we are developing now. I'm not going to show how we did it, but show the result. We do a solid body rotation test and a shallow water model test, and finally primitive equation model test. This is the solid body rotation to see the mass source going across the North Pole. if we look zoom to see it across very well. This is across the South Pole. And zoom into see. This is the shallow water model test. Put a ringing vortex and then use shallow water model. You can see this scheme is quite well. And finally, this is the primitive equation. This is a Sanhu Typhoon case. You can see that this is the initial time, 24-hour forecast, and 48-hour forecast, and 72-hour forecast. This okay. The left-hand side is the spectrum model, and right-hand side is the semi-Lagrangian model. You can see the pattern is quite similar, but system is quite weak for this semi-Lagrangian model. So finally, I will going to show you the high HPC we are using in CWB now. We have a three years installation of this high performance computer. The first year we have 81.2 teraflop compute capability. Second year this year we increased to 162. Next year we were going to 1,200 teraflops. And this is the final report. The final slides. This figure shows the scalability of CWB-GFS in this Fujitsu FX10. This is the core. This is the core number we use, and this is the speed up. You can see the speed up is quite well, and normally we use this 384 can meet our requirement is about 5,000 seconds. So okay, this HPC is quite good, I think. Okay, this is my presentation.
Okay, I'll take one short question.
Okay. Just one quick question. When you increase your number of layers from 40 to 60, do you see a change in the precipitation or convection or vertical profile or whatever?
No, I didn't see because there somebody was looking. I just take care of the dynamic, and so there's people who will see this. What you say?
Yeah, let's thank our speaker again.